Hello everyone, hope you're doing well. I was trying to run a custom diffusion model, basically a diffusion policy on a custom robot. During my attempt, I witnessed some weird and strange behavior that I would like to share with you. During my first attempt, I actually did a custom URDA for my system and then ran it on a Gazebo simulation and collected few episodes. By few I meant 100 episodes. After collecting those episodes, I trained them in a diffusion policy provided through LeRobot framework. But the problem that I faced is that during my experiment, especially my initial experiment, the model wasn't working properly, to be frank. If we have a look here, the model doesn't seem to know anything, although I ran it through 100 different episodes. So I was a bit frustrated and thought something was wrong with the code. But during a deep dive into the diffusion policy, I witnessed something different, some strange behavior to be exact. During my investigation, I saw if I change the distribution of the action, then the diffusion policy actually works. What do I mean by that? Let us see. This is an example of a completely changed model. By change, I mean this is an example of completely changed distribution. As we can see, it seemed to work pretty well. So before understanding what is wrong with our diffusion policy, first we need to know how diffusion policy came to be. It was originally inspired from diffusion models that were used in image generation domain. As we can see from this graph, a set of image can be described by an underlying complex distribution. The task of a diffusion model is to basically understand this distribution. So whenever we want to generate a new set of image, it basically samples from this complex distribution. How we can describe this process? It's quite simple. We basically start from a clean image and then gradually add noise in it until it becomes completely corrupted, a pure Gaussian noise. The main task of the neural network here is to learn how to denoise it until we get a completely clean image. As we can see, the forward process can be described through this mathematical expression q of t minus 1. The main target of the neural network is to learn this reverse process. This whole procedure can be explained through a Markov chain. There are two ways a network can denoise the sequence to get this clean image. It can do conditional denoising and it can also perform unconditional denoising. During unconditional denoising, the network actually predicts the value of xt minus 1 given the value of previous noisy distribution. During the conditional denoising process, the network again predicts the value of xt minus 1 given the value of previous noisy step under the condition O. This condition O can be of any type of signal. Usually in diffusion models, this signal comes from text embeddings. In the domain of robot learning, this diffusion policy is implemented by learning the action space rather than generating image. So our main target is to learn the complex distribution of the action space. Let us see how this happens. The procedure or the algorithm is similar to that of image generation, but the main target becomes different. In the case of image generation, our main target was to generate a 2D grid of pixels. But in the case of robot learning or behavioral cloning, our main target is to generate action sequences. So how do we do it? We initially take a random Gaussian noise distribution and we denoise it step by step, similar to that of image generation. During our denoising process, we train a neural network P of theta with the condition of observation. What is this observation? In the case of robot learning, our observation comes from the image. Usually we use web cameras or any type of camera to know the current position of our robotic apparatus. This image is then fed to a image backbone network. Then the generated tensor or embeddings are fed as the conditioning signal. So our main target is to denoise the randomly distributed action sequence and denoise it until we get a clear distribution format as that can be seen here. So we can see how this diffusion model came to be a diffusion policy, and then we implemented it in robot behavioral cloning. But an important aspect to see that every step our neural network actually learns to denoise the action sequence step by step. So if our action sequence have very high changing rate or very sharp edges, our neural network struggles to predict the next denoise step. What do I mean by that? Let us see. In order to understand our whole process, first we have to create our environment and all the coding sequence. For this experiment, I utilized ROS and I used Gazebo simulation. For ROS, I use ROS1, hence the overall project is based on Python 3.8. But sadly, our model was developed using Python 3.10 plus. Hence, we cannot use the whole framework that is provided via LeRobot. We need to develop some of our own code that mimics the behavior of LeRobot framework. We developed the ROS environment. We built the URDF. We simulated it in Gazebo. Then we trained our model using the training data. Finally, we used Kaggle inferencing and Grok, ng-grok API to connect our Kaggle instance with our local host computer. Finally, we have simulated our whole policy in the Kaggle environment and run our simulation in local environment to see the behavior. As we can see, we have two different cases of data collection. For our case 1, we use the Gazebo RQT library to develop 3 sliders, and we manually slide those sliders to collect data. When collecting this data, we can clearly see that our data has some high peak values with respect to time, meaning the data changes its trajectory very sharply. Although it may not seem such a big deal, but when we actually train our neural network or our LeRobot diffusion policy, we may see an exceptionally bad model. As we can see, we are collecting the data, and then after that, after training, we have run the inferencing. As we can see from this video, our model tries to push this blue box towards this red box, although it fails miserably. Not only that, our model seems to have some really sharp and high edges during its action sequence. Let us observe again. We can clearly see that our model is trying, but it fails to converge to a proper rollout. Now let us observe our second case. During our second case observation, we took our training data differently. We developed a custom leader robot. In order to keep the cost down, we developed it using popsicles and some potentiometers. For a 3 degree of freedom robots, we used 3 potentiometers, and as can be seen from this video, the data collecting process resulted in action sequences that are much more smoother. Does this smoothness affect our behavior or our training? Let us observe it. As can be seen from this rollout video, our model seemed to properly guide the blue box towards this red region. Let us observe it again. We can clearly see that our model not only delivers the blue box towards this red region, but it also knows how to use this or utilize this gap to this robot's advantage. We can clearly see that it understands that this is a gap region and utilize it to push this blue box towards this red region. It's certainly an intelligent behavior. Just by changing the distribution of our action, we can clearly see, using the same set of episodes and same number of steps in the training process, we get a much better behavioral cloning. Finally, we want to understand why this is happening. Here we can clearly see why this behavior exists. The author acknowledges that the CNN-based diffusion policy is much more easier to implement, and the training also converges much more quickly. But there is a problem. In practice, the CNN-based backbone will work with most of the cases, but however it performs poorly when the desired action sequence changes very quickly. This is our main target. After going through the main paper, I was able to understand why my training wasn't converging properly. If we go through the paper more, we can see the time series diffusion transformer based implementation can handle this complex behavior. But however, the transformer is more sensitive to hyperparameter and faces difficulty in training. So there is both good and evil present in this type of implementation. So why our training didn't work in the first place? The reason why our training didn't work in the first place is that we actually used the code from LeRobot implementation. If we go through it more carefully, now we are going through the code. If we look closely to the original implementation that is available in the LeRobot GitHub page, we can clearly see that the implementation only uses the CNN-based model. So whenever we're actually using the LeRobot framework, we have to be very careful about what our training data distribution is. The LeRobot framework does not provide the transformer-based implementation, and hence our fast-changing training data was not able to converge properly. So, in summary, the LeRobot only implements the CNN-based architecture, so we must be careful during our training data collection. Our training data must not have sharp edges. If we can mitigate the sharp edges of our training data, we clearly see that our model converges properly. Finally, after multiple experiments, I can conclude that the best performance was achieved when I used 100 different episodes using 512 by 512 size images with smooth edge training data. As we can see, if we reduce the resolution of our observation image, our performance degrades a bit, which is expected, but by reducing the size of image, we can also reduce the lag between the inferencing sequence. Another interesting thing that we can clearly see that the number of episodes do have an effect on this success rate. Why does it happen? The main reason is that if we reduce the number of episodes, it is much likely that our model will face an out of order distribution and would not be able to converge to a proper solution. And as expected, when our training data was very sharp using 96 by 96 image, even after using 100 different episodes, the success rate was poor and nearly 0%. In all these experiments, I used 9,000 steps to train the diffusion policy. Thank you. I hope this discussion helps you and you will be able to train more complex diffusion models without losing your mind.